All right, folks. So Thursday, we talked about taking a geometric series, which is a sequence that is developed by using a common ratio. So you start with a first term, and then you multiply that by some common ratio to get the next. And then take that next term and multiply by that ratio again to get the next term. And then take that next term and multiply by the ratio again to get the next term. We keep doing that as long as we want. On Thursday, we talked about taking that sequence and adding it together, so putting plus signs between it, and that becomes a series, okay? Now, in some geometric series, if R is a negative number, what's going to happen is that your plus signs are actually going to bounce back and forth between plus and minus, okay? Because you'll take, so let's say if I start with -1 as my, well, let's say like -3, just to make it a little bit more interesting. Let's say we start with -3 as our first term. And then let's say that R is -1/2. Then what's -3 times a -1/2? It'd be 3/2, right? And then a 3/2 times a -1/2 will be -3/4. And then -3/4 times -1/2 will be a +3/8. And it'll be a -3/16. And it'll keep going on and on, right? So if that's the sequence when R is negative, then the series will be -3 plus 3/2 plus -3/4 plus 3/8 plus -3/16. And if I have a plus a minus, what's adding a negative the same thing as? Isn't adding a negative the same thing as subtraction? So do you see then how the negative or the minus and addition signs alternate back and forth? Okay. So that'll happen if your R value is negative. You'll oscillate back and forth, which it's no big deal. But because people will say, well, I thought I was doing a sum of these series, but there's pluses and minuses. Well, if we talk about 3 minus 5, usually we talk about that as a difference, but it's still a sum. It's just a specific type of sum. Does that make sense? Okay. So just keep that in mind as you see some of the problems. There's nothing wrong with the plus and minus signs bouncing back and forth. So last week we talked about how if we have a sequence that is geometric and we want to add the terms together, okay, we can do that with this formula of a sub 1 times 1 minus r to the nth over 1 minus r. And that's when we have what we call a finite geometric series. Finite means you know how many terms are in the list. Okay, it's countable. That's what the word finite means, countable. Okay, so we did a couple examples. Okay, I think most of our examples had between 8 and 12 items in the list. Okay, now we had a procedure that was pretty elongated in regards to finding the logarithms, because we had to, when they don't tell me what the last term's position is, all right, so if the list was elongated and we, this first one says we were going out to 3,072. I don't know what term that was in the list, and we had to go through all that stuff on the left hand side that says log 1024 over log 2, all that stuff. Okay, that was kind of a pain in the butt. Okay, maybe we'll do this at the end to see if we can come up with a tool that will allow us to find that a little bit easier. Okay, actually let's do this now. I'm going to work on Desmos here and see if we can develop a quick way of taking this list and finding out what that number in the list was. Okay, so if we go back and look at the formula that we use, I don't know why Desmos isn't. Oh, I want the graphic version. Okay, so we have A sub n is equal to A sub 1 times R to the n minus 1. That's our formula. Okay. Now, what we have here, this here is our A sub nth term. Okay. So I'm going to type in right here is that A sub n is equal to 3072. So that'll be something that we can change here in a little bit. Okay. Our R value is 3. R equals 3. That was the oh man, this stinks. Okay, so R, I'm going to actually, because the way that GeoGebra or Desmos is programmed, R is a different type of equation. It's called polar equation, so I can't use R. I don't think, but I'll just leave it right there like that for now. So I'm going to try to build this with you, and then I'll just give you guys the URL so you can use this. So what happens eventually is that we take this, so we needed what right here, so this was 3 times 2 to the n minus 1. This 2, I'm sorry, this 2 is our R. I got it backwards. 2 is the R. And A sub 1 was the 3. So I'll rewrite that A sub 1 right here equals 3. All right, so what happens then is that this right here, basically I'm trying to figure out a formula for this rule right here. So I'm going to say n is equal to log. Now the way I got this 1024 is that I took the last number that we had, the A sub n, the 3072, and I divided that by log of R, which R was 2 in this case. And then we added 1 to that. Let's see. Now I have to redefine some things here. But this is the formula that I'm looking for. A sub n, so I need to know what my last term is. So we'll keep that 3072. Okay. Now this R is a problem because of what it's doing here. So instead of calling it R, let's call it, let's say D. See if that works. D is equal to 2. Oh, so it's A sub n divided by A sub 1. There we go. All right, so what this is doing, so basically what I'm trying to show you here is that this formula right here, or this expression that we came up with on Thursday, that number was always found by taking your last term in the sequence that you're going to try to figure out its position. And you divide it by the first term. Okay? So 10, if we look at the first term was 3, and the last term was 3072. If we divide those, that's how we get 1024. Okay? This term right here, this number, was the common ratio. Okay, so in this case 2. If I add 1 to that, it tells me n. And we found on Thursday that in that particular problem, n was 11. So if I look at the way I've coded this, does that give us n equals 11? So what we have here now is a program that will go through all of this work for us, and it will tell us, let's say for this one here, okay, I want to find out this nth position, which we found out on Thursday was 10. Okay, so there's 10 terms from 4 all the way up to 1 over 20, 1/28. Okay? I'm going to see if I can get the same 10 here. So what I do is I type in right here, a sum n, that's the last term, so 1 over 1/28. Okay? The difference, so it's the ratio. Okay, so, because it didn't let me use R, so I got to use D here. So I'm going to use 1/2. And then I got to type in my first term, which my first term was 4. If I type in all those things correctly, see what it spits back to me. Spits back to me n is 10. Does that make sense? So if we can capture those values, the last term, the common ratio, and the first term, it will tell you how many terms are in that sequence. Okay? And actually, let's see if I can actually rewrite this as R. Okay, that's better. R sub 1, so we don't have to use D. All right, so R sub 1 stands in for ratio. All right, so I'll send you guys this. I'll share this. I'll send it to your email. So that on your, because I know this process, hopefully we can do it because we spent quite a bit of time working with logarithmic equations last month. But it can be a hindrance. Okay, and I don't want that to be the hindrance in us being able to use this pretty simplistic formula to find that sum. Okay, so I'll give you that. Now that was working with a finite series. Means I have a group of terms that I can apply. I can say that this is the first term, this is the second term, this is the third term, all the way up till every single term has a position. If I have what's called an infinite geometric series, that means I cannot count them. That means that I have a list that I cannot complete. Does that make sense? I cannot, because of time constraints of just the existence of the world. There is no geometric series that has ever been written out in its entirety. Okay? Think about this. If I have a geometric series, let's just take the geometric sequence or series of taking 1 as my first term and then divide it by 2 to get the next. So I'd have 1 and then 1/2, right? I have 1/2 and then 1/4, 1/4 and then 1/8, 1/8 and then 1/16, 1/16 and 1/32, right? So that's a pretty easy sequence to develop, correct? Just dividing by 2, okay? Or multiplying by 1/2. Even though that is very simple to make, that series or sequence, however you want to view it, has never been written in its entirety. If the first person ever living would have tried to start writing that out, they would have died at some point and not finished the series. And then the next person that was alive picks up their pencil and starts finishing the series, they will die as well, and that series will not be finished. Does that make sense? And every single person that's ever been born and that ever will be born follows that procedure. That series would still not be completed. Does that make sense? So it's infinite in length, okay? But what's interesting is that even though we don't know what that entire sequence or series looks like, because it's never been written down, and it goes on forever, we can still add them up, okay? Which I'm not going to get into right now, the algebra of why this works, okay? But it says an infinite geometric series with the first term a sub 1, and as long as the common ratio is less than 1, okay? Now it says absolute value is less than 1. So basically what it's saying is as long as your ratio is between -1 and +1, okay, then that infinite list of numbers added together will add to what we call a finite sum, a number that we can put our hand on. Does that make sense? Okay. So let's think about this. If I take the series, let's just say it starts with 1, okay, and it goes to 1/2, and then it goes to 1/4, and then it goes to 1/8, 1/32, 1/64, 1/28, 1/28, 1 over 256. And I take that sequence and then I start adding them together. Okay, so the idea of that would be, let's see here. Okay, take 1 plus 1/2 plus 1/4. Whoa. Okay, let's say that I take, now it's only out to, I don't know, maybe 10 terms here. Okay, 11 terms. The R value was 1/2. Okay, as I add the next one here. Okay, so look at this number right, 1.999511719. If I take that exact same sequence or series and add the next term, so the next term is going to be 1 over 4,096. Did it change this thing a much? Look at the difference in those. The difference comes at that 5 and that 7, right? Okay, so that's tenths place, hundredths place, thousandths place, 10,000ths place. If I add, let's take this one here and add the next term. So the next term is going to be plus 1 over, so it'd be 4096 times 2, and there I get that. Okay, so I made that 7 now go to an 8. Okay, if I add the next one, it's going to be plus 1 divided by 4096. It'll actually be times then 4. Okay, now I got that one. Is that number much bigger than that number? It's not, right? But what happened? So we're going through this. That 5 was a 7 here when I added one more term. That 7 then went to an 8 when I added one more term. And that 8 went to a 9 when I added one more term, right? And now when I add one more term, this 3 is going to grow to something bigger. Maybe a 5, maybe a 7, maybe a 9. And then when I add another term, the next value that is highlighted to the right of that will eventually grow to a 9. Does that make sense? Because I keep adding smaller and smaller amounts, correct? Okay. And when I keep adding smaller and smaller amounts, okay, if these were in decimal form, what you'd be doing is you'd be adding, let's just think about this real quick. And now I know this might be a pain in the butt to write some of this down, so hopefully just watch here. If I take 1, okay, and then add to it 1/2, so now I'm going 0.5, and now add to it 1/4, so I'd be looking at 0.0 or 0.25, and then 1/8 is 0.1 0.125. That's what 125, and then 1/16 is 0.0625, and then 1/32 is 0.031. Try to get these lined up. 0.0312. 0.0625, and then the next one will be 0.015625, and the next one will be, so this will stop here, 0.0782125. And as you see, as you add these together, if I'm adding straight down, okay, eventually, so these three are the only three right now, because all the other ones are zeros, right? Those are the only three that are going to impact at this moment until we get these to add together. But those three are the only ones that are impact that 10th place, right? Because these rests are zero. These five are going to only be the ones that impact that 100th place, because beyond this, every number after this one will be a 0.00, and maybe even be another zero there. Does that make sense? So as I go further and further in the list, I'm adding smaller and smaller numbers whose 10th place, 100th place, 1000th place, 10,000th place are zeros. So then the only thing that's impacted, and as we get back into, I'll show you in this Desmos here, as we get and start adding, you know, this number right here, okay, basically that number right there is telling, because this is, that 8 changed to a 9, is that last number in that series, this number right here, has a decimal of 0.00000, maybe 3 or something like that. So it's a lot of zeros before we see a non-zero number. So what we're doing is we have a sum that is established, a bulk of this 1.9 number is established from the first 3 or 4 or 5 terms in that series. But then the end decimal places are getting manipulated, getting changed by adding these smaller and smaller values. What do you think this is eventually going to get to? Is this number going to, we've got an infinite number of things we're adding together. An infinite number of things we're adding together. Does that number look like it's going to go to infinity? Because that's what a lot of people think. If I have an infinite number of things, no matter how big those things are, then when I add them together, because there's an infinite number of them, I'm going to have an infinite amount. Does that make sense? Okay, and that's usually how people logically think about this stuff, which makes sense, I think. But that's not really what happens. Okay? If I have these series that are getting smaller and smaller values, even though there's going to be an infinite number of these smaller and smaller values, they don't accumulate to enough to move the needle past a certain value here. What do you think that 1.99999 number is going to eventually get to if I add up all of my infinite values? It's going to add up to 2. Okay? Now, the formula here to generate that is right here. Okay? So it's an infinite geometric series with the first term a sub 1, common ratio that is between -1 and +1, has the finite sum of this. It's a very simple formula. You take the first term, okay, and then you're going to divide that by 1 minus r. So our r was 1/2, right? So 1 minus 1/2. That gives me 1 divided by 1/2. Well, 1 divided by 1/2 gives me 2. And that is my finite sum. Take an infinite number of values in which I get each next value by taking the previous and multiplying by 1/2. If I have that infinite list of values and I add them all together, you're going to get 2 back. Okay? That's called an infinite geometric series. Now, if that does not happen, if your R value, so let's say I was going to, like, say R was 2. Now just think about this. If R was 2, so the first term would be 2, second one would be 4, next one would be 8, next one would be 16, right? Add those together, I get that. Okay, do that sequence again. But add the next term, you get 62. Add it again. But add the next term. You get 126. Keep doing that. By adding the next term, where is that? Are these numbers anywhere in relation to one another in regards to like what this one here was? These numbers, you could see that they were slowly approaching 2, weren't they? Do you see these slowly approaching any number? They're just getting bigger and bigger, aren't they? Okay? And that's because the common ratio was bigger than 1. Okay? If your common ratio is between -1 and 1, you will have a finite sum. If it's outside those values, you will not have a finite sum. And basically what that means is that the sum of this thing, the sum of this sequence that would look like this, okay, goes on forever, would go to essentially infinity, okay, or negative infinity depending on what r is, okay, and that's called or that idea is referred to as this, okay? So when the series does not have a finite sum, we say it diverges, okay? When it has a finite sum, we say it converges. Jenna? Well, one's on the positive x-axis, the other one's on the negative. But regardless, so if all those, so if I started with like an r value of like -2, then when I add all those up, it'll give me negative infinity. But regardless, and there's a lot of calculus that's actually involved as we dig deeper into this stuff to find out that infinity value, whether it be positive or negative. But this says when the series has a finite sum, it says the series converges. What's the word converge mean? A couple months ago, I was driving out of the teacher lot, and Julia almost converged with me. Yeah, they cross paths. They almost hit. They come together, right? Okay. What's diverge mean? They go away. So I took evasive action, and I avoided her reckless driving, and we diverged, right? All right. So what happens? So why we call this converges and diverges? If we were to look at a graph, okay, and I say that the x-axis, okay, like that stands in for the first term, that stands in for the second term, third, and so forth. If we were to graph these, what we find out is that when we add them together, that horizontal line of 2 and this line of the graph, they are going to come together. Does that make sense? They're going to converge, okay? If they were to diverge, they would go complete opposite directions, okay? And that's a calculus concept. But if you get a finite sum, we will say that the series converges. If you do not get a finite sum, if r is outside of -1 and +1, then you say it diverges. So those are little quantitative, qualitative questions that they might ask you in your homework. I'm going to post this section. I think it's section 9.5. Is that what it says up top? 9.5? It is already posted? Okay. Whatever the due date is, I'm going to add a day to it. Okay, so give you a little bit more time to work on that. So I'll do that here in a little bit, but I guess it is posted. You can work on it. But the due date will be one more day from the due date that is posted.